Good afternoon to everybody. So today is very memorable day or auspicious day, we can say. So we cannot start any event before thanking our teachers, right? So in whichever positions we are, there is the important role played by some people in our life, and that is our teachers, right? Except or apart from parents. So wish you all a happy Teachers' Day to my teachers, my colleagues, and also to the future teachers, right? So we are all here today to celebrate the Teacher Day in that sense. And what can be the best other way to celebrate Teachers' Day in academic environment other than this, right? So we have a distinguished guest with us, Professor Navakanta Bhat from IISc Bangalore. We welcome you to the DISR, and also our Vice Chancellor, Professor B.J. Rao Garu. And along with him, I request Professor K.C. James Raju, Dean School of Physics, and Professor M. Ghanshyam Krishna, Head CASEST, to take this chair. So now I'll request Professor Ghanshyam Krishna to introduce the CASEST to the audience.
Good afternoon, everyone. Happy Teachers' Day again. I think we'll repeat it a number of times. Professor B.J. Rao, Vice Chancellor, Professor Navakanta Bhat, our distinguished speaker for the day, Professor James Raju, colleagues, students. So it is indeed a very happy day today. When we wrote an email to Professor Bhatt requesting him to deliver the distinguished lecture, he gave us 2-3 dates. And we, as soon as he said he's free on September 5th, we sort of caught him and said, please come here on September 5th. And we are very thankful that you have agreed to come on the Teachers' Day. So I think that is special for us. CASEST is a center under the School of Physics. It was established in 2014 as a successor to the electronics program. We have 8 faculty members. We work on semiconductor devices, VLSI design, neural networks, optimization algorithms, system on chip, high frequency materials and devices, and many, I think between the 8 of us, we cover most of microelectronics, VLSI and semiconductor devices. We offer 2 MTech programs. One is called the MTech in Integrated Circuits Technology, which is our flagship program, which is under a little bit of a threat right now, but it continues to be a flagship program for us. We started in 2003. And in 2019, we introduced the MTech in Microelectronics and VLSI design. And the speciality of these 2 MTech programs is that we have a small fab which we were able to set up about 15 years ago under the Nano mission. And we give all the MTech students hands-on experience on device fabrication for a semester. So this has enabled us to produce good quality human resource in the area of fab, which is unique to at least the university system. And I know IISc has a very strong program on device fabrication and so on, but ours is a small, modest program. We have produced about 200 MTech graduates who have experience in device fab and so on. Apart from that, we have a PhD in electronic science and engineering, which is open to BTech graduates and MTech and MSc physics and so on. So we, as part of the PhD program, we are also able to do interfacial research between science and technology and so on. So we have produced, we are working on different kinds of things like, as I said, semiconductor devices in general and VLSI design and so on. Right now we have about 25 PhD students and slightly over 40 MTech students. We also run a number of skill development programs in in these areas. And we started modestly last year. The aim is to expand it over the next couple of years to become a hub for skill development in fabrication, microelectronics and VLSI. That is our parallel sort of stream of expertise that we're trying to exploit. This is a very brief introduction to the center. We are here to listen to Professor Bhat, so I am not going to spend too much time. Professor Sabat told me that I should thank IOE, but I am not sure how I will thank IOE. But as head CASEST, I will thank the IOE for funding this. So on this lighter note, thank you again for coming here and accepting our invitation. Thank you.
With your permission, I just want to add one more line. The CASEST got Chip to Startup program by MIT. So that is also one of our flagship program. We are now aim to design ASIC. We are all into the FPGA kind of thing, but we are aiming now to ASIC in SCL, Chandigarh. We'll talk more about that later. Okay, so although we have 8 faculty and 8 different areas we work together, but the sensor is the area which teaches us all together in the single thread. So it's good for us. Now I'll request Professor K.C. James Raju, Dean School of Physics, to address the gathering and introduce school to the audience.
Good afternoon. Once again, wish all of you a very happy Teachers' Day. And respected Honorable Vice Chancellor, Professor B.J. Rao, distinguished speaker, Professor Navakanta Bhat, Professor Ganeshan Krishna, head CASEST, my colleagues, students, and friends. And of course, in fact, School of Physics represents a lot of integration. We have 2 centers with the school. One is this CASEST, and about which just now Professor Ganeshan Krishna introduced. In addition, we have Center for Earth, Ocean, and Atmospheric Sciences. Apart from that, within physics itself, we have condensed matter physics, both experiment and theory, optics, again experiment and theory, and then this high energy physics, that is mostly theory at present. And we have experimental condensed matter physicists involved in CASES itself. And upcoming areas are also there, for example, soft condensed matter physics, quantum technologies, and these things are coming up. But when it comes to today's topic, in fact, it is about sensors. That is, just as Professor Sabat told, it is a much bigger integrating common theme across the university, because sensors is an area in which there is a lot of involvement from chemistry and life sciences is required. But and a lot of science, chemistry and life science work goes on in the country, which are very useful for sensors. But what is lacking is integration of them into devices and making the associated electronics and integrating that electronics with that sensors. That is something which got a major boost with sense coming up in IISc. Around that time only our clean room activity also started through Nano mission. But of course, in fact, our activity maybe, the funding wise, maybe could be around 5% of what was gone into institution like IISc. But our activity is also proportional to that. But we have the seed. But this sensor activity in this university, we have a lot of potential with a lot of life science related activities and chemistry activities in the chemistry. But that integrating with the electronics to make it a functional and packaged device, that is the key. And there, in fact, IISc has taken a lot of lead, and that is what that way Professor Navakanta Bhat's talk today is very relevant for us. We will have a lot to learn, and as a university, we will have a lot to contribute in this direction future. The integration aspect, which is very important, that invariably requires microfabrication activity. That is also of late started getting more attention in India. It will take off, but anyway, we have a seed. We have to develop further, and this, especially the aspects like why certain things are to be integrated and why miniaturization is better. These things are getting better appreciated these days, and nowadays sensors are getting into every realm of life, especially into health sciences and biomedical care, and more soon we will see them getting integrated into mobile handsets. so that our handsets will be a mobile laboratory. Therefore, for that, much more level of integration and functional integration and integration with the electronics is required. Therefore, that way it is a very exciting area in which as a university will have a lot to play, and especially for students who are learning now, they will be seeing these things, various concepts coming into reality in their lifetime. Therefore, it is a very important area where university can, as an entity, can play a lot of role. Therefore, we are very happy to have this topic on this Teachers' Day and on this first distinguished lecture of this CASEST. Therefore, we are looking forward to the talk by Professor Navakanta Bhat. Thank you.
Thank you, Professor James Raju, for giving a nice introduction about the topic and also telling the things happening in the University of Hyderabad. Now, I'd like to request our guest of honor, Professor B.J. Rao, Vice Chancellor of the University of Hyderabad, to address the gathering.
Good afternoon to all of you. I want to specially applaud Professor Navakanta Bhat ji for sparing his quality time and visiting us in person on a Teacher's Day. And I want to thank IOE for sponsoring this program. As usual, IOE sponsors very, very unique and very impactful programs, and this is one of those. I want to thank James Raju and Ghansham Garu for putting together this wonderful program with Sabath's catalysis. And this is a beautiful day for me in many, many ways. Firstly, CASEST was a nano venture in the university system, far ahead of its times. Before anybody in the university ecosystem, perhaps even in institutional ecosystem, thought about it, Hyderabad University thought about it and set it up with an intention of giving hands-on training in fab activity. I think this is ahead of time's invention. And I'm very fascinated by that model that university set up. And another dimension is setting CASEST within the School of Physics is another venture. Absolute winner, in my opinion, because deeply this is physics. The physics in the nano world. Because all of you are familiar with physics at atomic world, physics perhaps at a molecular world, in hard and soft condensed matter, but this is physics in nano world. It's very different. So putting it in physics actually serves a lot of good purpose. So School of Physics actually was set up with its intention, which is ahead of its times. So anything that was done ahead of its times will have a deep value, and we must cherish that. So this is a side take-home that I want to just articulate. Coming to the topic today, sensor scaling for smart nanoelectronic systems. It's a very pregnant topic. There are so many things in it. For me, the take-home is whenever we talk about nano, that's a beautiful meeting point for biology, chemistry, and physics. That is how I look at it. That is the only point where these three really unify, the Trimurtis. And a fantastic science will emerge. So that is a real beautiful thing. And if that beautiful nano system, if it becomes highly biocompatible, I think the power gets scaled up. Because anything that you do that is useful in terms of sensing can be put into body and can be used for interesting physiological measurements. So biocompatibility is an additional power that comes into it. And of course, scaling is the ultimate power, if you can scale it up. Scale it up into cost-effective models will be even better. So you can see that many winners are coming in together there. So it's quite beautiful. And I would think this is a bottom-up approach of designs, not top-down. Typically, sculptors do top-down. They come, take a rock and chisel away unnecessary things and come up with a design top-down. by removing unnecessary things. And then there is a beautiful design. But this is a beautiful example of bottom-up assembly systems which attain powerful functions like sensors and other interesting. In fact, one can use chemistry to its hilt and design properties almost to your requirement. This is what people say. You can design properties to your requirements. So it's a very beautiful world that is getting unfolded. It's a very, very competitive world, and IISc is doing extremely well. I just learned from him that on the average, per year, they train about 500 to 600 hands-on trainees from fab facilities. And that's a great contribution to the country. I'm sure probably this is the highest volume that they're generating in terms of hands-on training, which is very much required for many, many national activities. Of course, we started small and we stayed beautifully small. I think we also will scale up, and the idea of bringing Professor Bhatt is to give that impetus. Whatever help you and your ecosystem can provide us in scaling up, that would be a real welcome step, because we have large number of students who are roaring to go. So once again, thank you very much for coming and giving us a glimpse of interesting world, and hopefully we'll stay in touch more. You are also part of our IOE, management board, governing board. So we are connected in more than one ways. Thank you very much. Namaste.
Thank you, sir, for giving such an excellent insight into the topic. We are on the journey of scaling up, sir. Right. Now the much awaited things. It is my privilege to introduce Professor Navakanta Bhat, who received his BE in Electronics and Communication from University of Mysore in 1989, MTech in Microelectronics from IIT Bombay in 1992, and PhD in Electrical Engineering from Stanford University, Stanford in 1996. Then he worked at Motorola's Networking and Computing Systems Group under Advanced Product R&D Lab in Austin, Texas, until 1999. At Motorola, he worked on logic technology development, and he was responsible for developing high-performance transistor design and dual-gate oxide technology for PowerPC microprocessors. He joined the Indian Institute of Science, Bangalore in 1999, where he is currently the Dean of Division of Interdisciplinary Sciences and Professor at the Center for Nanoscience and Engineering, CENS. His current research is focused on nanoelectronic device technology, biosensors for point-of-care diagnostics, and gas sensors for pollution monitoring. He has more than 300 research publications in international journals and conferences, and 50 international patents to his credit. He was instrumental in creating the National Nano Fabrication Center, NNFC, at IISc Bangalore. It is benchmarked against the best university facilities in the world. He has served as the chair of the NNFC Administration Committee during 2010 to 2015 and chair of CENS during 2016 to 2020. We are privileged to have you here, sir. He is an elected fellow of all these bodies like IEEE, INAE, IISc, INSA, and NASI. He has received the Young Engineer Award in 2003 and the Indian National Academy of Engineering Swarna Jayanti Fellowship in 2005 from the Department of Science and Technology, Government of India, and Professor Satish Dhawan Award in 2005 from the Government of Karnataka. The list is too big, I will shortcut it now, right? He also got Nina Saxena Technology Excellence Award in 2018, and NASI Reliance Industries Platinum Jubilee Award in 2018, Birak Innovator Award in 2018, and Distinguished Alumnus Award IIT Bombay in 2022. He has also received the most prestigious Infosys Prize 2018 for his contributions in engineering and computer science category, and Yasraj Raj Bharati Samman for innovation in healthcare in 2022. Apart from this, he was the member of the Board of Governors for IEEE Electronic Device Society, EDS, and also the Vice President of Educational Activities, IEEE EDS, Electronic Device Society. He was the chair of IEEE EDS Nanotechnology Technical Committee during 2017 and 19. He was the editor of IEEE Transactions in Electronic Devices 2 during 2013 to 2015. He was the chair of the Human Resource Development and Infrastructure Committee of the National Program on Micro and Smart Systems. He was also the member of the committee set up by the Principal Scientific Advisor to Government of India to recommend strategies to develop semiconductor manufacturing ecosystem in India. He is currently the chair of Vision Group on Nanotechnology of Government of Karnataka. So they are all his awards and credits. So that means he was an excellent researcher, and also he is the industry itself, right? I'm coming to that. He is the founder and promoter of a startup company, PathSoth Healthcare Private Limited. Based on his group's research in biosensors, PathSoth has developed the first of its kind multi-analyte point-of-care diagnostic device for multiple chronic diseases, including diabetes and its complications, anemia and malnutrition. Along with that, kidney and liver diseases, and also COVID-19 antibodies. For this technology, PathSoth has received multiple recognitions, like CII Industrial Innovation Award in 2017 for the most promising startup, and 2017 FICCI Healthcare Excellence Award in 2017 for the best startup of the year, and Design Impact Award for social changes by Titan. We are most privileged to have you here, sir. So you are at a stretch, academician plus industry in one single goal. We are all eagerly waiting to hear from you about the sensor scaling for smart nanoelectronic systems. Now we request you to take over and give the lecture, sir.
Very good afternoon to all of you. Firstly, I would like to thank Professor B.J. Rao, Vice Chancellor, Professor Ghanshyam Krishna for inviting me here. It's indeed a pleasure to be here with you on this auspicious day, which is Teachers' Day. You know, I didn't think about this coincidence that happened, just given a few dates, and Professor Ghanshyam chose this date. Typically, every year I would be in IISc on Teachers' Day. I would never miss that. But, you know, this is the first year I'm away, and I think, you know, I'm glad that I'm here, right? I've been, you know, one of the IOE management committee meeting that was chaired by Professor Rao as a Vice Chancellor, and I was privileged to see great initiatives taken by the leadership of the university. And I hadn't had a chance to visit, and I hope that this is one of the many more visits, you know. Although we have interacted, Professor James Raju, under the national program on, you know, MEMS, there was a lot of interaction with the University of Hyderabad. So, the Vice Chancellor mentioned there are many keywords here. For students here, I think one of the message that I want to also give you is from the keyword, one of the keyword here is interdisciplinary sciences, right? So I happen to be heading this division, interdisciplinary sciences. This was a 6th division which was started in IISc about 15 years ago with the recognition that look at any science and engineering problems, they invariably require interdisciplinary efforts. And with that vision, this division was started. And for students, you know, I think it's time for us to come out of these silos and not call ourselves just physicist, chemist, or biologist, or electronics engineer, and what have you, right? We need to, of course, have the depth, but we should also be able to appreciate the breadth, and that's where new discoveries and new inventions happen. And going forward, I think it will be even more important. So I thought I should also highlight that. I will touch upon that during my talk. You know, I will begin with the big picture in my talk, and specifically talk about two research areas that my group has pursued over last couple of decades, and that has been made possible by excellent students, postdoctoral fellows, and many collaborators I have had the privilege to work with, and of course the funding support from various organizations. So I would also like to acknowledge that at the outset. So I have a couple of slides just to tell you that this is really a national facility and it is open for any of you to come and utilize that. It is not just to say for the sake of it, it's being implemented, right? So I thought I should highlight that. This is the Center for Nanoscience and Engineering that came into being in 2011. This is what was mentioned, one of the largest academic fabs in the country. And hence it is not IISc's property, it is not even department's property, right? It is property of the nation. And indeed, let me just skip over that. We run a national program, a national network program called Indian Nano Users Program. Through this program, we have made these facilities open to any researcher in the country. And what you see in the map here is the number of organizations, not the number of researchers, that have utilized the facilities at this center. And the number of researchers over the last about 10 years is more than 8,000, right? And 8,000 researchers from across the country have come here and have gotten trained. And that's, I would say, an amazing, democratization of facility, if you will. Because this is a new culture, right? I mean, if you want to create a scale, a different kind of scale of human resources, you really have to work in networks. That's the only way you can build scale. And, many of them could complete their theses, PhD theses, for instance, because of these facilities. And they, in turn, have generated many top-notch research publications and patents. In none of them you see anybody from IISc as co-authors, right? So that was also a policy decision we took, that there shouldn't be any conflict of interest. And that's why there is such a momentum now that there's a lot of users who want to come and utilize that. And this program is now running in third phase. Actually, look at, a state here. I mean, we have sort of touched many districts in the states, right? So that's the point I wanted to highlight here. And also gone beyond tier 1 and tier 2, even many tier 3 institutes have been benefited because of this kind of a program. So I do hope that, in addition to using your own facilities, if there aren't some equipment that are available, you're always welcome to come and utilize those equipment in these facilities that have been set up, right? So that's the message I wanted to give. So let me come to the topic today. I'll begin with where we have come in the context of electronics. Electronics is again a highly interdisciplinary effort, essentially making of a chip. There is physics, there is chemistry, there is material science, there's of course electronic circuits, computer science, and so on and so forth. Only when you really bring all of them together, right, you will be able to make a chip, right? For example, I always tell this to my students, that Intel, which was one of the first semiconductor chip company, right, which started this whole revolution of electronics, it was the Gordon Moore, the Moore's law that you hear about, was actually a PhD in chemistry. He was not even an electronics engineer, right? So that is how there are no boundaries really, right? So you should really be thinking in that direction. Then I will essentially sort of mention that we haven't given the same attention that we have given to compute and storage systems. The attention to sensor system is long overdue. I think there is a need to really look at this in a holistic fashion, right? That is the reason I have titled it as sensor scaling. The scale has two different contexts here. I'll come to that in a minute. And I'll give a couple of examples, one on nanobiosensors and other one on chemi-resistive gas sensor. Again, you see that this is really cutting across different domains. Right, so in terms of electronics, we have come a long way from the very first transistor, semiconductor transistor, which was essentially discovered by physicists at Bell Labs way back in 1947, to the first integrated circuit that then came about in 1958. And as I said, Intel, which innovated and introduced the first computer on a chip. That's what we call them, microprocessors, right? That happened in 1971. I mean, look at that. At that time we used to have about a couple of thousand transistors. Today, the state-of-the-art chips today have billions of transistors in them, all at nanometer dimension. We talk of today not just 7 nanometer. Today we are talking of 5 nanometer technology and even going beyond the 5 nanometer technology, right? So this is, very interesting and very amazing, science, engineering, all coming together in unison and making this happen. So if you look at, there are two different things that I wanted to highlight here in terms of the scale. We have reduced the feature size or the dimensions of the building block of electronics, which is transistor. Transistor used to be of the order of tens of micron in 1970s, and today we talk of nanoelectronics, nanoscale transistors, right? There's a reduction of dimensions, which we call feature scale, almost 1,000 times. Now look at the other scale, right? This is complexity management. We used to have a couple of thousand transistors earlier. Today we have billion transistors, tens of billions transistors, which is 10 power 7 increase in scale if you think about. Only because you are able to do that, the amazing functionality come out. All your chat GPT and large language models will not run but for the underlying compute and storage systems that are built using these nanoscale technology with gigascale integration. That is happening as of now, right? So going forward, as I said, we need to look beyond computation and storage. This is what I call, we have come traditionally, technology drivers have been memory and computation engines, right? We have increased the storage density. Today on your USB drive, you can store hundreds of movies, right? Because you can get terabyte kind of storage, right? And also computation, very, very fast computation, right? And that will continue to happen, of course, in future. And that's why what I call traditional scaling path. This will not only be driven by silicon. Silicon, of course, is a workhorse of semiconductors. But there will be a lot of very interesting new materials coming in. That's where nanomaterials will become extremely important. In addition to the technology, which is digital CMOS technology today, complementary metal oxide semiconductor technology, there will be many, many new technologies, including what is called neuromorphic computing. I will touch upon it very briefly. And quantum computing. Now, Government of India has just launched a quantum mission in the country, right? All these will continue to happen. But there is another vector here, which is what you can call equivalent scaling path. Here, reducing dimension is not only the objective, right? You also want to put in many, many functions. It's called functional integration. You want to have many, many materials, sensors, chemical sensors, biological sensors, inertial sensors, all sitting along with your compute and storage engine, right? So that is how the future systems would look, right? So, today we have computers which, this year for our convocation, we had Vishwanathan Anand as the chief guest. That's why I thought I will put this slide here. He said these days, chess players don't even worry about competing with computers because it's not interesting. Computers will win hands down anyway, right? Because that's just a brute force. They have a lot of database, they churn out a lot of computation, and they come out. But I'll come to it in a little while. But they really consume huge amount of energy to do that. That's not as efficient as biological entities do it, right? So I think going forward, we really have to look beyond this, right? We are building all these compute engines, but contrast that, just a data center will consume billions of watts of power. Now, human brain, their building blocks are neurons. Again, tens of billions of neurons, about 100 billion neurons, let's say. And of course, it is not deterministic as we build the chips. It evolves stochastically and adopts. And most beautiful thing is the power consumption is about 20 watts, right? It can beat any modern computer in terms of energy efficiency. So the new vector that is emerging even in computing, we cannot continue to do the computing as we have been doing the digital way of computing, right? There is a new vector which is called neuromorphic computing or brain-inspired computing, right? A lot of work is happening in this direction. At IISc we are also working on what are called memristor devices. These are new devices unlike transistors. Memristors have memory, and they're called memory elements like neurons, right? So they sort of mimic neurons. So now can you use such devices and build computational systems, right? So that is a new vector that is emerging. And in addition to that, there's also, as I said, a lot of interest in quantum computation. The future compute and storage systems will have bits, which is digital electronics. It's not that we will, do away with that. Everything has its place in the world, right? One size doesn't fit all. So bits, qubits, and neurons. Neurons as in brain-inspired computing. All of them will come together and will give you a seamless computing which will be far, far more energy efficient compared to what we are doing today. Maybe you don't have to charge your cell phone for a month. How great that would be, right? So, but we cannot even imagine that today, right? We can do all of that only if we can learn from nature and try to think about, mimicking that and building the systems, right? But we are still stuck in computing and storage, right? What are smart nanosystems? Smartness is really going beyond computation and storage. It's really being aware of environment and adapting to the environment. And how can you do that? And in addition to, again, look at the living beings, right? We of course have computation and storage, engine, that is brain, but we have sensory organs also, right? And they're extremely important, right? So the key is really we can only be able to do smart systems by having a lot of sensors, right? Not just one sensor or two sensors. Very, very large number of sensors, millions of sensors. You may ask, why do I need millions of sensors? I don't even have few sensors today on a chip. Why are you talking about millions of sensors? I'll give you a motivation in just a minute. But yeah, so sensors and sensors, right? That is what I wanted to highlight. And again, it's going to be very, very highly interdisciplinary. That is the kind of field this is all about. And they will, of course, all the buzzwords that you hear, AI, robotics, smart factories, all of that will be enabled by sensors working in conjunction with computing and storage. Just computing and storage will not be sufficient, right? So why do you need million sensors? Again, let's look at one of the greatest biological systems that has been created, the olfaction, right? Which is sense of smell, right? We have nose, we smell. We know about that. But let's start digging a little deeper. If you go inside the nose, biologists call them as receptors. There are a lot of receptors, right? It's a 3D structure, not a 2D structure like a silicon chips that we are building today. It's about 10 centimeters square, and there are 6 million sensors, right? And it is the diversity of these sensors, 6 million receptors which are sitting there. That gives us an amazing olfactory sense. What is it? We really don't appreciate that. I want to highlight this. There was a very nice study that was published in Science, and Nature picked up that and created this story out of it in 2014. This analysis was done, and it says human nose can detect 1 trillion odors. Right? We never imagined that we have that kind of capacity, right? And that is possible simply because of the integration of 6 million sensors. Right? And that is the motivation for you, right? That is why we want to miniaturize the sensor and have the scale, large number of sensors, millions of sensors coming together and working in unison. And again, in biology, if you look at other olfactory systems, Professor Rao is an expert here, but look at airports, we don't use humans, right? As a sniffers, we use dogs because we have 300 million receptors there, which is even more evolved compared to human olfactory system. We have only 6 million. It has 300 million sensors, right? And that is why, you have that kind of power. So imagine having an electronic nose or a nose on a chip, right? We cannot do it with just computing and storage elements. You need large number of sensors, right? That is the motivation. So, given that we need to do this, future nano systems, smart nano systems, will have to be massively parallel sensory engines like what we have seen in nature, in biology, operating in conjunction with computing and storage engines, right? So with that background, let me just spend next half an hour or so on two case studies that I will discuss based on the work that we did in our group over last several years. One in the context of biosensors, with an eventual goal of creating what we call lab on palm. The other one is really what I told you, electronics nose. That is in the context of gas sensors. Of course, there is electronics here, but there's a lot more than electronics, right? There's not just silicon electronics, there's also printed electronics, flexible electronics, 3D systems that I was talking about. And there is electron movement, but electrons don't necessarily move only in semiconductors. They also move across the barriers, right? So there are what are called redox reactions as well, right? This is something the chemists use very often, but that is where you start discovering some new applications, right? So again, you need novel materials, devices, and of course eventually build systems. About 2 decades ago, when I started looking at this area of point-of-care diagnostics, health diagnostics, the question that we were asking was, can we bridge the healthcare divide, right? Diagnostics is the first touch point in healthcare systems. You need to do the disease diagnosis, right? Only then you can do the treatment administration, therapy, and all that, right? Now, if you look at the diagnostics technology, just as a computing technology, communication technology, it has also evolved. Early 1900s, diagnostics labs in the hospital used to be like really chemistry labs. They used to take blood samples, urine samples, do a lot of titrations, and really come up with a lot of very interesting papers published way back in early 1900s about detecting molecules in blood, urine, and so on and so forth, without using any sophisticated instrument, but just using some titrations, right? But subsequently, just as many technologies evolved, especially in 1980s with the introduction of immunoassays, today you go to any pathology labs, you see what are called all these autoanalyzers. Oftentimes the person running these equipment doesn't even know what is happening behind this equipment, right? You load the sample, there's some analysis that is done, immunoassay or whatever assay, and out comes the result, right? They're very accurate, but they also need very controlled ambient, right? I mean, it's very, very difficult to have such systems at scale, let alone villages, even in tier 2, tier 3 towns, right? It's very, very difficult, right? So what next, right, in terms of diagnostics, right? So that's where World Health Organization says you really need to build systems that are available, accessible anywhere, and affordable, more importantly. These are the 3 A's that WHO enunciates. And this was really the motivation factors, and we really started focusing on diabetes, but over a period we have sort of gone beyond that as well. In the context of diabetes, everybody knows glucose measurement. You can buy these glucometers in the pharmacy stores today, but mere glucose testing is insufficient for diabetes management, right? There are many other markers that need to be measured, right? For example, there's a gold standard that endocrinologists use, which is called HbA1c, right? Glycated hemoglobin, which gives you 3 months average sugar load on your body, right? And that is what is used for control and management of diabetes, because all complications of diabetes go exponentially as your HbA1c level increases linearly, right? So typically HbA1c level, which is essentially the part of your hemoglobin which is complex with glucose, should be of the order of 5%. If you have 100 hemoglobin molecule, only 5 of them should be complex with glucose. If you have more glucose in the body, more hemoglobin would like to complex with glucose, and that's the increase in your glycohemoglobin, right? And as that happens, if it goes to 10, 11, 12%, your risk of kidney diseases, your risk of diabetic retinopathy, all of that increase exponentially, right? So the question that we were asking, can we come up with a point of care HbA1c sensor, right? Actually, in all proteins go through glycation. Albumin is another protein in plasma, which is also very abundant. And in some cases of diabetes, glycated albumin is a better marker for glycemia, right? So the point was really to come up with a platform technology which can be expanded to take many, many more sensors, right? As and when we come up with the right solutions, right? So that is how we started with this notion of building what is called a lab on palm. And today we have many tests that we have been able to develop, going from discovery to scale up to regulatory approval, deploy in the field, and so on and so forth. But this is really a technology which can accommodate many, many more sensors, right? That is what I was starting with, really to bring in many, many sensors on a single platform, right? In a summary, this has been a very long story. Anything that you really want to work on and bring about some difference, you have to be at it for a very long time. We started this research way back in early 2000, and through many generations of PhD students. Shivrama Krishna was actually the first PhD student. You know him very well. He's a faculty at IIT Hyderabad here. And eventually by 2015, we had come up with many discoveries and also had filed many patents. We thought this is time to really translate, because oftentimes what happens is you come up, you publish, and it just stays in papers, right? So we thought maybe we should take the next plunge, and that's when we started working with the clinicians. And this device and many more versions of this device, as I will show you, is actually now being in use, right? But how did it start, right? I'll just give one or two examples. This is electrochemical sensing. As I said, glucometer, Professor Leland Clark is called father of biosensor. He came up with these glucose oxidase based electrodes, which are now used almost in every glucometer. There are two parts to it. One is, of course, the electronic reader, which gives a display, sometimes with all these fancy things like Bluetooth connectivity and whatnot, these advertisements that you see. But really the heart of it is this sensor, this disposable sensing strip. You measure, put a drop of blood on this strip, and instantaneously this sensor will magically tell you what is your glucose concentration. How does it happen? Dissect it little further. This strip of plastic really has this printed carbon lines. We call it an electrochemical cell. It has 3 lines, right? An electrochemical cell has 3 electrodes, right? So, we call them working electrode, reference electrode, and counter electrode, okay? Working electrode is where the redox reaction, electron transfer reactions happen. You apply certain potential to the working electrode with respect to reference electrode. Because of the electron transfer, a current flows between working and counter electrode. The idea to have the counter electrode is not to disturb the redox potential, right? So that's why we apply the potential between reference and working electrode, right? So that is what we do. In terms of glucose sensor, for example, this working electrode is functionalized with a receptor, an enzyme, glucose oxidase, which is very specific to glucose. What I mean by that is, this glucose oxidase enzyme, blood has many, many molecules in it, glucose being one of them. That is what I am trying to sense. Glucose oxidase would oxidize the glucose into gluconic acid. There is an electron transfer in the process. In principle, I can try to pick up those electrons by having a working electrode and applying a potential. But that's a very sluggish reaction. And hence we use what are called mediators. We use a mediators which is invariably a ferricyanide couple, potassium ferrocyanide couple, which acts as a shuttle between this electron transfer and the electron transfer at the working electrode. And this accelerates, this is like an amplifier in the context of electronics, right? And hence, this, you apply a particular voltage, that results in this electron transfer. You measure this current, right? So you get oxidation peak and reduction peak, and these currents are directly proportional to the concentration of the analyte that you are trying to sense. So far so good. So now the question is, so why don't we have other sensors for other molecules that are very important in the context of diagnostics? So, there have been many publications, very humongous work that has happened, but still we only see glucose sensors, right? And there are many review articles that have been published, and all of them sort of point out to the inability to come up with these receptors, what are called biorecognition molecules, which will specifically interact with the analyte in question, at the same time produce a signal which is detectable either electronically, optically, or by any transduction mechanism that you can think about, right? So that is what we started looking at. Just give you an example with albumin sensor. Look at albumin. As I said, albumin is a very important protein in the body. It has about 585 amino acids. However, there is no redox active metal structure in albumin. Unlike hemoglobin. Hemoglobin has iron center, which is redox active. Okay? Whereas in albumin, you cannot tease out anywhere any electronics. So for all practical purpose, it's like an insulator. So there is no way I can build an electrochemical sensor out of it, right? So, this is just an example as to why things have not progressed, right? We have not been able to, develop very good sensors. Professor Rao was talking about bottom-up discoveries. In fact, we call all our sensors as physiology-inspired sensors, right? When we started looking at this problem, then we started reading a lot of biology literature also, right? And we discovered that this albumin molecule has been characterized so well in biology that it is actually called a molecular taxi, meaning that it binds to a whole range of substances. Many drugs that we take, including paracetamol, for instance, first albumin binds to them and then it sort of transports it to the rest of the body, right? And that's a phenomenal function it has. Then the question that we asked was, now can we leverage this and come up with a sensing modality? And then we discovered that, copper, in terms of binding affinity, has, one of the highest binding affinity to albumin. Okay? It is almost 10 power 16 per mole, right? That's huge, right? So we said, okay, based on this understanding, can we come up with the following hypothesis, that we know that albumin binds with copper. Of course, I cannot take out any electrons from albumin, right? But I know that copper is an excellent redox material. Copper is used even in electronic chips as an interconnect. So what if I build a sensor now, unlike a glucose sensor? I'm not going to use a glucose oxidase enzyme, but I will use some copper salt, right? Of course, devil is in the detail, as they say, to come up with the right salt, with the right pH, so that the binding is absolutely perfect. It took more than a couple of years for us. But hypothesis is that if you can put a copper salt there, and then if you put your blood drop on top of it, blood will have plasma, it has a lot of albumin in it, albumin will bind copper. Now, copper is a very light material. Again, remember, electrochemistry is diffusion-mediated reaction. Okay? Albumin is a very heavy molecule, almost 65 kilodalton. So what it means is that all copper that is bound to albumin will have extremely slow diffusion. It will not even reach electrode. Only the free copper will be available for you to do redox electrochemistry. So then the hypothesis was that if that is the case, with increase in albumin concentration, you should get a decrease in current, electrochemical redox current. Right? I mean, this is how you start your discovery and scientific hypothesis, right? And hence we said, okay, if everything goes well, you have current as a function of albumin, I'll calibrate this, I have an albumin sensor, right? But as I said, the devil is in the detail. You don't obviously go and start working on a blood or plasma. You first buy a simple albumin molecule from Sigma and, have a very simple buffer, NaCl buffer, and just see whether you can do a, simple electrochemical reaction and whether this hypothesis is indeed true or not, right? And actually, as we started, venturing into copper chloride, we looked at many copper salts, copper sulfate, and so on and so forth. In every case, we got a consistent redox current trend. With increasing albumin concentration, you have a decrease in current, right? That was very encouraging, right? So then, of course, even to get this proof of concept, it takes a lot of time. Then you have to go to blood. You need to, work with clinical partners, and that takes a lot more effort. And, you need to do a lot of validation, statistical validation, and so on and so forth. But to cut the long story short, this is how you start from a discovery and you go all the way to really doing something which can be validated in the field, right? And similarly, we have also been able to do this for hemoglobin and glycated hemoglobin and many other analytes also. But let's see if maybe, okay, hemoglobin, as I said, is a very interesting molecule. It has this iron moiety in it, right, which is redox active, and hence it has attracted electrochemists for many years, right? The only thing is it is not accessible. You need to first take out the globin chains, right? You need to, if you put hemoglobin or blood in alkaline solution, you can get rid of these globin chains, right? And then you can try to do a redox reaction here. But when you do that, you do get a peak, redox peak there, but it turns out, the current quickly saturates. Actually, at hemoglobin concentration which are extremely small, of the order of 0.4 gram per dl, which are not physiologically relevant, because even for anemia, your hemoglobin concentration is of the order of 7 to 8 gram per dl, right? So, which means there is something that is fundamentally happening here, where your electrochemical reaction is being inhibited, right? So again, we started trying to dig deeper, and then we found out that, there's a lot of literature again here in the context of what are called hemichromes, where it is said that, when you have this hemoglobin in alkali solution or even, aqueous solution, you can start forming dimers and tetramers. It's like forming a polymer, right? And if that happens, it blocks the electrode surface, right? And that means, if your concentration starts increasing, then you will quickly saturate and you will not be able to, do the detection, right? So that was a big problem, and that is when, in the literature we could find that, hemichromes are interesting molecules where the 5th and 6th coordination site of iron, right? The 4 sites, as I said, in hemoglobin are already bound with the proteins, right? It's bound not with the hydroxyl ions, but with amine entity, right? Amine coordination will ensure that there is no dimer and tetramer formation, right? And that's why they were able to see a very nice reversible redox reaction. So the question that we asked was, can we this was studied in the context of naturally occurring hemichromes in the body, right? So we asked the question, can we recreate this, in lab? Can we convert hemoglobin into hemichrome, right? And again, go through a experimental protocol, and this can be done, using heterocyclic chemicals such as imidazole or pyridine. You add that to your blood sample, and that will ensure that the hemoglobin is converted into hemichrome. If that happens, you have excellent reversible redox reaction, right? So redox reactions become extremely reversible, and they tend to be linear, extremely linear over a very wide range of concentration of hemoglobin that is physiologically relevant, right? So we were actually able to come up with the hemoglobin sensor using this technique, and of course, eventually it has to be a dry chemistry, I mean, those are the details, but let me skip that. The next question is glycated hemoglobin, right? Glycated hemoglobin is only a fraction of the hemoglobin which is complexed with the glucose, right? It is expressed as the percentage of the hemoglobin which is complex with glucose, which means you need to measure two different things. You need to measure total hemoglobin and you need to measure the fraction of the hemoglobin which is glycated or not glycated. One is complement of the others. If you know the total, you subtract one, you get the other, right? So that is what we did again using a very, very complex assembly on this plastic strip or a sensor that I mentioned. We had multiple films which had different chemistries there, which would ensure that I either measure total hemoglobin in one case and I measure non-glycated hemoglobin in other case, because I trap the glycated hemoglobin by filtering that, and then I would be able to express the glycated hemoglobin as a fraction of the total hemoglobin, right? So this we were able to do very successfully. So then, as I said, we went on to sort of build this whole electronic systems, which, as we said, lab on palm in a single device, you can do these multiple tests. And during COVID, we were also approached by DST, because they knew that we had this platform for the non-communicable diseases. They said, can you sort of repurpose this for COVID, right? And this was a very interesting experience for us. Everything was shut down during COVID, including labs in IISc. Only if you say that you're working on COVID technology, you would be allowed to work. And that's how we started this work. We came up with this idea of having, again, a disposable test strip, electrochemistry. And, within 9 months, we started from a proof of concept all the way to, validating this proof of concept, doing very, very, rigorous clinical trials, and eventually, bringing it out as a product which is approved by the regulatory agency, right? So this is something we do. Now, as we speak, you need to continuously evolve and innovate. We have now come up with something called, the first device that I showed you, lab on palm, we call it Anupath. This we call Anupath Nano series. Nano series meaning it's even more miniaturized compared to what we had earlier. Again, it has multiple tests on a single device, right? So it has been used, as I said, we actually call it diagnostics at your doorsteps. It's being used in 12 different states and in many, many contexts, in very, very remote areas, right? These are some field images where clinicians and NGOs have been using this very successfully, right? So that was one part in the context of biosensor. As you could see, there are many, many things there. There's biology there, there's chemistry, there's a lot of engineering, electronics, and eventually if you want to build a product, you need to put all of them together. You need to attain the scale, you need to have a manufacturing. Today we have a manufacturing facility where you can manufacture something like 1 crore tests per month, right? Because these are the tests that are required in very, very large scale, right? In fact, now Government of India has, under the National Health Mission, they have a program called Anemia Mukt Bharat, right? So we are hoping that some of these technologies and products that we have developed will really be utilized in a very large scale going forward. So the other part is the electronic nose, which is to do with the chemi-resistive gas sensors. This is again another very interesting technology where we use semiconductors, but not silicon, but metal oxides. These are metal oxides such as tin oxide, for example, or there are many other metal oxides, which have a property that when they absorb certain gases, right, the conductivity of those metal oxide changes. Okay? That's why it's called chemi-resistive sensor. And this adsorption is also a redox reaction. There's oxidation and reduction reaction, which again depends on your partial pressure of gas that you have in the ambience, right? So you have a semiconductor, either N-type or P-type. You have an oxidizing gas or a reducing gas. You have a change in resistor, increase, decrease, depending on what combination that you're looking at, right? And it's essentially a two-terminal device. right? You just measure a resistance and calibrate that resistance. So there are many figure of merits. One of them is, of course, response. What is the change in response for a unit resistance that you have, or change in conductance for unit conductance. Again, here our emphasis is not to build one sensor, but really to put together as many sensors as possible. We started taking baby steps. We started building this sensor array with 4 elements. 4 element sensor in a 1 mm square area, where we had zinc oxide for carbon monoxide, barium titanate and copper oxide, tungsten oxide, and vanadium pentoxide, right? Each one customized to sense different gases, right? Now again, all of this was done through microfabrication technique, and also bringing in the right kind of material deposition and characterization. A lot of things go in there. We have programmed with the ISRO, where they have interest in launch vehicle site monitoring in Sriharikota, and these are the devices which have been deployed there for sensing a variety of gases, such as hydrazine, which is their fuel that they use, oxygen, which is an oxidizer, NO2 is also an oxidizer, hydrogen, of course, is also a fuel, right? So again, here you start from your basic materials, physics, and go through developing the technology, and eventually you have to build a system, and the system has to be rugged so that it sees the light of the day. It can survive in the extremes of the ambience where it has to operate, for example, right? Because example, in Sriharikota you have extreme humidity, right? And your sensor has to work over the range of humidity conditions also, right? And we are also trying to look at enhancing this. We are now looking at building a larger sensor array. Maybe here 30 elements are there. Each element, there is an electronics signal processing, as well as there is a sensing material that is put on top of this sensor pixel. You can call it as a pixel. Each pixel is sensing using a particular sensing material that is put on that pixel, right? Now, depending on which gas that you have, you can start looking at its response, and you can, just like we learn how to smell, you can train these sensors. You can train this sensor array. This is where all your ideas of neural networks and machine learning and all of them could be adopted here, right? So you have unique signature for different gases. You can train these sensor networks, and thereby you should be able to build a very complex system, right? We are looking at a variety of materials. You need new materials. Recently we have also been looking at 2D semiconductors. There's a lot of effort in 2D semiconductors for a variety of applications, including sensors, right? This is, for example, tungsten disulfide nanosheets, which were used for ammonia gas sensor, right? So when you introduce ammonia, the current changes. When you take out ammonia, the current decreases back to its value. That is what I meant by redox. These are reversible reactions, right? So only when the gas is present, there is a change. If the gas is taken out, it comes back to its original value, right? You can calibrate it, and you can actually come up with the right sensor. We are nowhere near what biology is doing, right? I was only showing you 30 sensors. We have to reach hundreds, thousands of sensors, right? But that's the vision, hopefully very soon, in the next 10 years or so. If you want to build a nose on a chip, you will of course need to have very high performance compute engine. May not be just the digital electronics, but maybe neuromorphic engine also, as I was mentioning earlier. Storage, of course, that is required. But then you need to have this whole sensing materials, array of sensing materials, very, very large numbers, right? Only when I can do, just as I'm doing so many billions of transistors, if I can do thousands of sensors here, then I'm good to do many, many applications which are impossible at this time, right? We don't have that technology. So this technology also requires, again, coming together of different disciplines. We cannot just do it using conventional silicon fabrication, photolithography, as Professor Rao mentioned, the sculpting, top-down approach alone will not take us there. You need additive technology. Right? These are more amenable for bottom-up approach. Right? Only if you can do that, printing, additive technologies, only then I will be able to have a scale of millions of sensors. Otherwise, for each sensor, if you do one lithography step, you are dead. It becomes so expensive, your process cannot be fabricated, manufactured. Right? So this is very, very, very interesting scientific and technological area which is unfolding, trying to firstly integrate sensors at very large scale and integrate them with computation, storage, and all other systems that you want to build for a variety of applications. We'll be only limited by our imagination in terms of application, right? So I think confluence of nanomaterials, electronics, sensors on a single chip, I think will enable intelligent and smart system, will revolutionize the future technology landscape. Right? Thank you for your attention.
Thank you for the nice lecture. In the gas sensing, you have used different materials for different gases. So the selectivity comes from that. But will the sensitivity be the same for all, or will it vary? How do you normalize, or how do you take care of that?
Yeah, a very good question. I actually did not have time to go over many things. Metal oxide gas sensors, while different materials have orientation towards some gas, selectivity, but they're not insensitive to other gases. There is always a non-zero cross sensitivity. That's the biggest problem in metal oxide gas sensors. Unlike the optical sensors, which are like signature analysis, right? So in fact, that is another reason why you need sensor array. Because it is, unless you use some filters on top, which are selective to a particular gas, that can enhance the selectivity. But that also becomes very difficult beyond a point. Because for so many gases, trying to come up with different kind of filter is in itself. You can come up with filter, but doing that filter at that micro nano scale is also a challenging thing. So I think the only way out there is to really have this diversity. Have many elements. Each element has preference to a gas, has non-zero cross sensitivity. It's okay. I can train that sensor array. And based on that, I would be able to infer. In my opinion, that's the only way to have the best sensitivity in selectivity in metal oxide gas sensing.
And about sensitivity, suppose one has a ppm, one has a ppb, the other has a ppt. Can we make uniform for all kind of gases, or how far are we from achieving that?
Yeah. No, the sensitivity is also another very important parameter. Depending on, again, application, each one needs particular, because there is you should remember that there is always a trade-off between the sensitivity and dynamic range. A sensor may sense in part per trillion, but then it will not have a dynamic range to do from part per trillion to
part per billion.
Few percentage, right? So, again, you need to see, if you want to, for example, detect toxic gases, there you need to have part per trillion. But if you say, for example, monitor carbon dioxide in the ambient, I don't need to go to part per trillion because my ambience itself is about 300 ppm. Now I'm asking a question there, whether it's going from 100 ppm to 1000 ppm. So it's an overkill to make a sensor of part per billion, let alone part per trillion, or even ppm, right? So each sensor you have to optimize the sensitivity. That is where nanostructuring will come again. Because you need to enhance the surface area. That will help you to enhance sensitivity.
Thank you. Thank you.
This is a real practical question. How would you attract PhD students in this program, what type of PhD students you look for? Because this brings in multiple aptitudes here. It's not
I
easy.
think one of them is sitting here. I just saw Shiva
So-
coming here from. Very good question. I think I don't know. I've been very fortunate to have some excellent PhD students. So I've not had the trouble in exciting them. Maybe I've lucked out. But I think once they see a trend, also, then people see that, okay, this is an interesting area, there's a lot of opportunity. I think getting early students like Shiva was very important. But now, it's easier. Thanks to IISc, absolutely.
Thank you, sir, for giving an exemplary lecture. It included right from atoms, image of atoms and transmission electron microscopy to the product level, which is very rare and the need of the hour. So it was even more interesting for me. I'm Professor Swati Ghosh Acharya from School of Materials, School of Engineering. I am from materials engineering background. So what we do, we make different kind of nanomaterials. From that we make inks, and from that we make these printed electrodes. And we use that for detection of toxic heavy metals in water. So the whole process, the challenges of it, and it is really very inspiring to hear you. So that is what I wanted to thank you for this lecture.
Thank you. And you mentioned printed inks. I think inks for printing. I think that is what I was alluding to at the end. I think that's going to be a very important technology, right? You really need to make these inks of different materials. If you can actually print it rather than having a very expensive photolithography techniques, right?
Yeah. Even the commercial printed electrodes, the disposable ones, are extremely costly. There's almost 400 per electrode. So that is very costly.
Yeah.
Thank you very much.
From students.
You spoke about those arrays in which you had incorporated some signal processing.
Correct.
So that is realized? Is it on silicon?
That is realized. It's on silicon. We actually realized it on a 0.35 micron ASM technology. It was done a few years ago, actually. So what we had was, this was a foundry technology offered through Europractice. We did, each pixel that you saw, we had the front-end electronics, which had an amplifier and sigma delta A to D converter, so that you can actually convert the analog signal into digital signal. And then what we did, we brought it out at the interconnect level, at the last interconnect level, and created a Wheatstone bridge, because Wheatstone bridge is the one of the best structure for looking at the differential sensing, right? So we created that, and we actually opened those areas in the chip and put the functional materials on that Wheatstone bridge interdigitated electrode resistance, right? So that is how we created that. So you had that Wheatstone bridge connection going all the way to silicon, which was the front-end amplifier, and then the other signal conditioning. The whole thing was implemented, yeah.
So the sense that after the Wheatstone bridge, it was done in IISc.
So Wheatstone bridge definition was done in the technology, because you go through the CMOS technology. Wheatstone bridge only had this interdigitated electrode. It had open circuit when we received them here. So what we did in IISc is, firstly we did the whole design. Design was taped out, you get the chip back, like the chip to system you are talking about. Then we did post-processing. We put our material on those Wheatstone bridge to create that resistors on the Wheatstone bridge, yeah.
Thank you for an excellent talk. I was wondering whether for electrochemical impedance spectroscopy, you have to functionalize your electrodes for each application, or is it like a one-size-fits-all? I mean, do you use graphitic electrodes for all of your applications. For example, hemoglobin and
Yeah. So the impedance spectroscopy came in the context of the chip that we made. That is where I think it had mentioned impedance spectroscopy. But currently, all the sensors, biosensors that we are using, which are productized, are in the market, they are either based on chronoamperometry or based on cyclic voltammetry. We are not using impedance spectroscopy there. Yeah, you could use, but simpler the better, right? Chronoamperometry is the best, but in some cases we have not been able to do that. We are using cyclic voltammetry. Right? Yeah.
Thank you.
Sir, first of all, wonderful the scope you are giving to the faculty as well as the students for research in multidisciplinary. Thank you for the talk. I'm basically in computer science department. So you are have given a scope, but mostly working in the level of the nanotechnology and this area of diagnosing the part. If we are looking in terms of the machine learning and deep learning, how can we get the data? Because most of we people are working on the existing data set from those things, and we may not able to reach to the present healthcare requirement in terms of the deep learning and other thing. And you people are working on this area. Is there any possibility that computer science people can work on your data so that better way analyzing of the diagnosis and all those things in terms of the healthcare point of view?
Yeah. So for that, actually, there is an initiative with ICMR currently running in IISc. Again, if you want to apply AI and ML, the problem also has to be a complex problem. Okay. In a problem like detecting a hemoglobin, you don't need to make it so complex. It's a very simple problem, right? On the other hand, let's say you have a chest X-ray and you want to do a disease diagnosis, right? Those are the applications because it's feature rich. There's a lot of information there, right? These are the conditions where you need to bring in AI and ML. Currently, there is a project with ICMR actually to create this open database. IISc is part of that, and actually IISc is leading that project of diagnostic images, right? It could be chest images, it could be ultrasound or what have you. Because here, the images are very rich, right? And that is where you may miss out things. Similarly, in the context of electronic nodes that I talked about, we are still not there. But when we build million sensors, you will have a very rich data from million sensors or even 1,000 sensors. Then you need, again, machine learning and AI techniques there.
Yes.
Right? But when you're just looking at one sensor, you don't necessarily have to worry about that.
Sir, my question is in collaboration of the research.
Correct. What
From
I'm saying is the
the
problem
university
that I was looking at hemoglobin sensing, if you made a reference to that, that doesn't need machine learning or AI techniques. That's what I was trying to say. Okay. Right? So only when you go to a problem which needs that, you need to bring in that. The problem, as I said, if you build an electronic node, certainly, at that time we would need a computer science techniques of AI and ML for that.
Yes, sir. Right. I have a small thought, maybe. So most of the present Indian women are facing the challenging problem as a thyroid. And still the testing process is consuming a lot of blood. And this is again leading to the anemic and other thing, and problem is continuing. Can the kind of the testing what we do in the sugar testing kind of thing, similar kind of device if can brought, most of Indian women will be saved. In this context, any scope? Thank you, sir.
No, I think you're absolutely right. I think there are many pressing problems we have to address. It is certainly possible. Maybe some researchers here can also look at it. It's doable, right? You just need some people, to work on that and take it to the logical conclusion. Yeah.
Any questions from that side, that cluster?
This is not a question. Although you said you did BTech in electronics, to me, like quietly, without telling anyone, you did biology major, chemistry major in Stanford. You are talking so fluently, all those things. To me, it appears like that. The question is like this
No, I
nano.
gave you other example. Chemistry, Gordon Moore doing electronics. So I think it's just the interest,
But that's the important message for our students. Always they are like, they think whether it is electronics like that. So it's very important thing, like for a message for all the students here. That's what I want to thank you. These nano heaters, when you are saying,
Yeah.
nano means like the heat, how much, what is the dimensions?
The dimensions we have done from 5 to 10 micron all the way going down to 0.1 micron, which is 100 nanometers.
100 nano. That is the size of the heater?
The heating element.
The heating element. But how heat dissipates on the surface?
That depends on, what is the area that you have, right?
Okay.
In some cases, we actually wanted in a very narrow area. That's when we made a small heater. In some cases, we wanted a bigger area where we have a meander of this heater, like a heating coil going around.
Okay, yes.
So it covers larger area.
So there is a lot of interest now in kind of micron size heaters.
Yes.
Okay, thank you.
Yes. It can be used for many other applications.
Thank you.
Last but one.
Thank you for an excellent presentation. I have a very simple question. See, in the nose, 6 billion sensors.
Million.
Sorry, I'm sorry. 6 million sensors.
Yeah.
Are integrated.
Pardon me?
Are integrated in its response, final response. Now you are going stage-wise, 1, 2, 3, 4, 10, 15. How do you make sure that we will reach?
I think that's amazing capability of human intellect, collective. I'm saying across the world, what has happened. The same thing started. If I were to take just comparison in electronics, we started with 1, 2, 10, 20 transistors. Of course, it took 5 decades to reach billion transistors, and I hope it will not be another 5 decades. But I think it is possible. It is a challenging task, but it is doable, I think. Maybe we need newer technologies, which will come in future with innovation from student body, which is sitting here. I think we have to be optimistic on on the capability of, I think it will happen. I'm confident.
Thank you.
Your question also sort of alluded to how long will it take, what scale. I could sense that also, but I would imagine hopefully in the next 10 to 15 years. That's my gut feeling. Yeah. Yeah. Right. Eventually, it's really to have this total integration also, right? That's why we are doing, just trying to mimic what biological system is doing. We have, by the way, done it. I should mention this. I talked about 5 sensory organs. In terms of vision, we have done extremely well. I mean, look at your cell phone cameras today. Billion pixels, right? I mean, it was unimaginable, right? I mean, look at that scale. But that has not happened in biology and chemistry, because that's more involved problem. Yeah. Correct. Yeah.
Okay, I think we'll end this QA session now. Thank you, Professor Navakanta, for giving the extended lecture. A big round of applause again. Now I will request our Vice Chancellor, Professor B.J. Rao, to give a small memento to Professor Navakanta Bhat. This is the CASEST embedded into the cube. This Charminar and CASEST both are there.
Very warm greeting and I think good evening to all. It is my privilege to propose a vote of thanks for and acknowledge the contribution of those who worked hard to make this event successful. Today we have gathered to mark a significant milestone, the Golden Jubilee year of the esteemed University of Hyderabad. This event, organized with great enthusiasm, is a witness to our institution's rich history and promising future. On behalf of the organizing committee, I give a really heartfelt vote of thanks to our distinguished speaker, Professor Navakanta Bhat, for accepting our invitation and spending his BGS time gracing the occasion. Today we had the opportunity to listen to you. The lecture was very informative, sir. Which included the sensor system for point-of-care diagnostics and environment monitoring. Both research areas are very important to our society in all respect. So our heartfelt thanks to go to our esteemed Vice Chancellor, Professor B.J. Rao, for his unwavering leadership, encouragement and extensive support. Sir, your presence here today, despite your busy schedule, is a true testament to your commitment to our university. Thank you, sir. I would like to thank Professor Ghanshyam Krishna, Head CASEST, and Professor K.C. James Raju, Dean School of Physics, for their continuous support and encouragement in all our effort. I would also like to thank Professor Sabat, the coordinator for Golden Jubilee Distinguished Lecture Program, coordinator for CASEST, for arranging this wonderful lecture. We acknowledge our gratitude to the Institute of Eminence for providing financial support to organize this event. I sincerely thank the entire audience for their valuable time, attention, and the interest to listen this lecture. Last but not the least, I sincerely recognize the continuous support of Mr. Ray Babu and non-teaching staff who have worked hard to make this event successful. Thank you very much. Okay. There is a tea outside. After that, outside, you can go and take that. Okay. Thank you.